Hello, everyone. This is Group 19 with our project, the Deliver Me Something. Here's the team. And our objective is to create a simple delivery drone. Essentially, the goal of the drone is to be able to deliver small packages, short distances across the planned for use across the UCF campus. So simply, between buildings, between rooms. And the idea behind this is to reduce the amount of time that reduce travel time essentially, so that people can focus on doing actual productive work and not have to worry about, going back and forth between a room or pausing what they're doing and potentially losing a train of thought or something. How we went about accomplishing this was through a use of a GPS, a compass, and a sensor, all combined together with a central microcontroller. Fairly straightforward, and the sensor is mainly used for obstacle avoidance.
Right here we have a full demonstration of our project. As we can see, it starts by self-orienting itself and calibrating the compass that it has incorporated, and it will self-orient towards the goal that we set for the GPS. We have an X marked as the destination spot for the bot to arrive, and then within a radius of 1.5 meters it will stop. Here we're measuring the distance from the destination to where it actually stopped. Here 1 foot, 2 feet, 3 feet, and 3 inches, which is approximately 1 meter in distance from the destination.
Hi, part of this, we're going over our engineering specifications. To meet our requirements, we believe in these three key engineering specifications, particularly obstacle avoidance, turn 90 degrees plus or minus 5 degrees when an object is in front. This is to help the robot in the future be able to avoid pedestrians, random objects that aren't calculated into the GPS locations. We have destination recognition. The objective of this is to stop within 1.5 meters of the goal location. This is to allow for the robot to stop at its desired location. And then self-orientation. This object allows for you to turn towards the goal direction plus or minus 5 degrees. This allows for the robot to optimally head towards the objective, to the desired objective. Shown here is the Spec 1 destination recognition. As seen in the top right, we have our white mark, which marks the destination, the desired destination. We ran this test multiple times and were able to measure the average distance from the target. As seen, we are allotting for a window of 1.5 meters plus or minus from the target, and we were averaging 1.45 meters from the target from our multiple test.
For our second specification, we have obstacle avoidance. And as you can see in the video, we have set up a little obstacle course for our bot to go through. And as you can see, the bot clearly avoids these obstacles without actually crashing into them. The rulers for the video were meant to designate the distances that we mentioned before. And as you can see on this chart, with a goal distance of 10 centimeters, so which means that the bot stops at least 10 centimeters away from the object, we can see that the average was about there. Is a little bit less than we desired, but that can be attributed to calculation time and time, the reaction time essentially of the bot, but it is acceptable for what we are looking for.
Next, we have the self-orientation for this object, we demonstrated that the bot will turn to the 127 degrees orientation. We can see that it did with the compass right next to it. So these are our test runs we did, and we did 10 of them, and we did reach an average of 127.5 degrees. So we had a window of 2.5 plus or minus degrees of accuracy for the bot turning, and this feature is mainly used at the beginning of the trajectory for the bot, so it can self-orientate towards the goal destination. Then we have the basic design that we created, and basically it includes a battery of 5,000 milliamps to keep the bot going for quite a little bit of time. We use one compass, one ultrasonic sensor, 2 motor drivers, 2 voltage regulators, so we can drop the voltage from the battery to the 5 volts that the components need, and the 7 volts for the motor drivers and motors. And we use one ATmega 328 processor for processing the data for the bot. Here are some pictures of our basic design on a breadboard. At the front, we can see the ultrasonic sensor. We can also see the compass at the top, and the 2 voltage regulators right on the side, and the 4 wheels with the battery underneath the breadboard. Here's a front picture, which you can see a little bit better all the components. This is a picture of our PCB, and so this is after the breadboard was tested and proved to work. We had a PCB design right here with all the components mentioned before. This is a small sensor test showing that if something approaches 10 centimeters of the sensor, it will send a signal, in this case, a LED.
The overall algorithm for our bot is relatively simple. We simply have the bot go in a straight line, which is the fastest way to get to its goal destination. If desired, the bot will perform the obstacle avoidance that you have seen in the previous slides, where the bot will sense an obstacle, turn 90 degrees, then proceed to move forward and keep going for a little bit of time. If it senses another obstacle, it will turn 90 degrees again, but after a few seconds of time, it will turn back left 90 degrees and check if that obstacle is still there. If it is, it'll repeat the process, and if it is not, it'll continue to move forward. The main language we used was C++, as it is what Arduino is mainly using, and the libraries that we used for this were TinyGPS Plus to help decode the GPS coordinates that are provided. We use the QMC5883L compass libraries designed specifically for the compass that we were using. We used the wire.h library, which helps implement I2C, and we used the NuPing library in order to code up the sensors.
The PCB design for this is shown right here. We see the schematic of a simple PCB design following 2 voltage regulators and the accessibility of 2 motor drivers, 1 ATmega, and all the other required components mentioned beforehand. Here is showing 2 different versions of the board, one showing the polygon section showing the ground plane, as well as the trace links running through the PCB itself. Here is one of the more updated versions of the PCB that we have learned from our previous experiences and allowing for optimization of the PCB itself, as well as the design of it. We overall, from earlier designs, eliminated a lot of different capacitors and the way they are along the board. And then we also implemented more surface mount devices to allot for a much cleaner and safer board layout. Is there any comments, questions, or concerns? Please ask. We'll be more than happy to answer them. Thank you for watching.